For this section, we're going to do related rates. Part one, there's going to be two videos for this section just because it's bigger. It's a lot more material. So for this chapter, we will be looking at applications in which every variable depends on time. This means that we will need to use implicit differentiation for each variable. So in the previous section, we learned how to do implicit differentiation, which basically we found the chain rule played a major role in that. So we're going to have to do that multiple times in each problem that we do. Okay, so let me show you what this looks like. So it says, suppose we are given an equation 3x plus y squared equals 16. I would like to find dx dt, which is read the derivative of x with respect to t, time. So the thing is I'm going to now, instead of doing ddx, I'm going to do ddt, meaning take the derivative with respect to time. Okay. So when we take the derivative with respect to time of 3x, the derivative would normally be 3, right? If it were ddx, it would normally be 3. However, because it's with respect to t, and this is not a plain old t, this is a 3x, we then have to say 3 times the derivative of x, which would be 1. I'm sorry, take the power, put it in front, rewrite the inside, reduce power by 1, and attach the chain rule. So then this would be dx dt. And again, we're going to use Leibniz notation for the remainder of this section. I guess you could call it x prime, but that doesn't really reveal x prime with respect to what variable. We want to make sure everybody knows we're taking derivatives with respect to time. So time is the relationship between everything. It relates all of these different rates. Okay, so we have 3 dx dt plus, now normally the derivative would just be 2y, but because it's with respect to t, we must attach the dy dt, and then this is 0 because that's still a constant. Okay, so now this would be technically kind of your answer, but I asked you to find dx dt. So what I'm going to do is I'm going to take 3 dx dt, and then I'm going to subtract the 2y over to the other side. So this is minus 2y dy dt. Okay. And then we're going to divide both sides by 3. So this would become dx dt is equal to negative 2/3 y dy dt. Okay. Now they normally would then follow it up with say they would say something like this. They would sign or say use find dx dt when y equals 3 and dx dt equals -1. So then what they would do is they would ask you to actually solve for dx dt, find the rate of change of x with respect to time when you know certain things. So this is our when information, and this is our other rate, dx dt, or I'm sorry, dy dt. Yeah, I don't know why I said dx, this is dy dt. So now I can substitute these values in. So now I have dx dt equals, and then it says -2/3. Now what's y? They said y was worth 3, and they said dy dt was worth -1. So the 3's cancel, and we are left with 2. And that would be what dx dt is worth when the rate of change of y is -1 with respect to time, and then y is worth 3. So it's very important that we talk about this when throughout this section. This when information can only be used once the derivative has been taken. Once you have taken the derivative of a problem, you can plug in your when information, not until after. Okay. So let's see here. All right. So I have a few steps that I want to go through with you guys. So the first step is so let's say suggested. And this is kind of a template. You guys don't have to do every single solitary step, but this is definitely a way I would start. And then as you develop, you can, kind of do it your own way. So suggested steps for related rates problems. Okay, and this is just a guide. Okay, so number 1, always read carefully the problem. Read the problem carefully. And draw a picture if possible. Not everything has a picture, but if it does, please draw it. It will help you. Okay. And you should be careful when you're drawing this picture to label things in the picture correctly, especially if you're dealing with constants. So maybe note, be sure what is constant and what is not. Okay, so that's just kind of a little important note. Okay, so step 2, based on your picture, what is known about the variables? So I would say a good idea is to list what you know. I kind of do step 1 and step 2 sometimes blended personally. So here's the big one. Write an equation that relates the variables whose rates of change you know, relates the variables whose rates of change you know, and the ones you are trying to solve for. And the rate of change you need to find. Okay. Step 4 is going to be differentiate the equation. So the equation that we just built or we wrote, we're going to now differentiate the equation. And then after you have taken the derivative, substitute in the appropriate info. Okay. Okay, step 6. Okay, this isn't really a step. I would say the when info. The when info should not be used until after the derivative has been taken. And then there's a lot of formulas that you guys will need. That's technically step 6, but I don't want to write all those out. You can ask about them in class, but in general, there's like the area of a rectangle, surface area, product, or not product, circumference, you know, all those formulas for shapes and stuff come up a lot. Volume of a cylinder, volume of a cone, those type of ones that are very strange and obscure formulas that aren't common, like you don't use them every day, those will provide to you. But other than that, or you'll have them in your notes anyway for the exam. So anyway, let me see here. So suppose a rectangle I cannot write today. So a rectangle's length is increasing at a rate of 3 centimeters per second. Okay. Its area is increasing at a rate of 5 centimeters squared per second. How fast is the width changing when the area is 10 centimeters squared and the length is 5 centimeters? Okay, so basically what I'm going to do is I'm going to draw a quick picture of this. A rectangle is definitely a shape that I know how to do. Okay, so we have our rectangle. Let's say that this has an area. This has our length. Let's call this our width. Okay, so now what we did is we drew our picture. Okay, it says read the problem carefully and draw a picture. So we need to figure out what we're trying to find. So step one, we drew the picture. Now let's write out the stuff we know and maybe label a few things. So it says a rectangle's length is increasing at a rate. So we're going to say, how would you say the rate of change of the length with respect to time? You would say dl dt, right? dl dt, and they said it's worth 3. And I'm not going to write labels because we know they're going to cancel out. So I'm just going to write 3. Okay. Its area is increasing at a rate of 5 centimeters squared. So we know that dA dt, the rate of change of the area, is increasing at a rate of change of 5. Okay. Now what do we want? We want to find d what? dw dt. We want to find the rate of change of the width with respect to time. So imagine that the length of this rectangle is increasing at a rate of 3 centimeters per second, and the area is increasing at a rate of 5 centimeters squared per second. Okay, so we need some information, or I should say we need to kind of figure out what, I don't know how to say, it's not what we're trying to find, because we know we're trying to find dw dt, but we're trying to find, I guess, differentiate between the when information and what's current information, so, or what's constant. So that says, how fast is the width changing when the area is 10 centimeters? So notice right here, it says literally the words when. So we know our when info would be A equals 10 cm squared. I'll just write 10. Okay. And the length L is 5. So this is the when. So we're not allowed to use this, and this is not constant, right? This is changing. We're not allowed to use this until after we've differentiated. Okay. So now we're to the point where we've kind of, based on your picture, state what is known about the variables. Okay. And it says write an equation that relates. So we're basically saying that we know the area equals 10 and we know the length is equal to 5. Now, if that's the case, if the area is equal to 10 and the length is equal to 5, don't I technically know the width also? I technically know that the width, let me write it over here. The width is actually what? Let me fix that. The width has to be 2, because the only way we can get an area of 10 if the length is 5 is the width must be 2. Okay, so technically I know all 3 of these. I know the 2 dimensions and I also know the area, but this is all when info. So what I need to do first is I need to set up an equation that relates area and length times width. Oh, I accidentally said it. We know the equation that relates is area equals length times width. Okay, so remember, I can't plug in when, I can only plug in constants. We don't have any constants right now. So what I'm going to do is I'm going to take the derivative of both sides with respect to t. Okay, so this will become dA dt equals, now we can't forget that this is a product, so we're going to have to do the product rule. So the derivative of L is dL dt w plus L times dw dt. Okay, so we have now taken the derivative, and it says right here, differentiate the equation. Once you've done that, you are now, after you have taken the derivative, substitute in the appropriate info. The when info can now be plugged in. So we know that dA dt from right here is 5. So this is going to be 5. dL dt is 3. So this is going to be 3 times W. But what was W? W was the 2 from the when info, right? Plus the length, which was 5, times dW dt, which is what we're looking for, right? We're trying to find dW dt right here. Okay, so now we just solve for dW dt. So this is going to be minus 6 minus 6. So we get -1 equals 5 dW dt. Divide both sides by 5. So this becomes -1/5 equals dW dt. So now we can bring the label back in. What was it, centimeters? Yep. So -1/5 centimeters per second. Okay, that's how fast it's decreasing. So the width at this moment in time is actually getting smaller by -1/5. -1/5 centimeters per second. Oh, I said it right the first time. Okay, so it's actually getting shorter by -1/5 centimeter per second. Okay, so this would be our answer. We solved for dW, and we, based on this problem, we now know how fast the width is changing as the length is changing and the area is changing. And again, all we did, and this, by the way, this means it is decreasing because it's negative. All we did was we said, well, based on this moment in time of this problem that was set up, I can now tell you that at this moment, that's what the rate of change of the width would be. Okay, let's look at another one. Okay, so let's see here. We got another one. It says a ladder 13 feet long is leaning against a house. Oops. Is leaning against a house. When the base of the house sorry you guys, it kind of threw me off. When the base starts to move away from the house. Okay. When the base is 12 feet from the house, the base is moving at 5 feet per second. How fast is the top of the ladder moving? Okay, so let's read this again. It says a ladder 13 feet long is leaning against a house when the base starts to move away from the house. So basically you have a ladder that started to slide away from a house. When the base is 12 feet from the house, the base is moving at 5 feet per second. How fast is the top of the ladder sliding down? Okay, so it says a 13-foot ladder. So this is important information. We need to know that. When the base, so right here it says when the base is 12 feet from the house. So that's important. The base is moving at a rate of 5 feet per second. So that's a rate. And then they want to know how fast is the top of the ladder moving. Okay, and if the ladder is sliding down, it's going downward, so we probably will get a negative answer, depending on how we set up the problem. So what I'd like you guys to do is try to use those steps that I provided and pause the video and try to draw your picture and kind of set up what you've done, okay? All right, so hopefully you unpause the video and you guys have this. So you have some house, right? Okay, I'll put a little window there. And then you have this ladder leaning against the house, right? Okay, so there's our ladder. And we know our ladder is 13 feet long. I'll write that in black. Okay, so we know, you know what, I'll even put little, so we know it's a ladder. Okay, I can't draw, but this is pretty amazing for me. Okay, so we have that. And I want to make it and kind of understand what they're saying. So this ladder is leaning up against the building. Without saying it, they're basically telling us that it is a right angle, because, you know, we hope that the ground is level to some extent. So we have this right triangle now. And a right triangle is very good because we know multiple theorems. We know sine, cosine, and tangent. We can use all that information. We know the Pythagorean theorem for right triangles. So we know a lot of information about this graph. Okay, so what I want to do is I want to write my when information. I think I used blue last time. So yeah, let's use our when info. Okay, so our when information is the base is moving at 5 feet per second. Let me see, the base is 12 feet from the house. So 12 feet. How do you guys want to write? So what I normally like to do is, if I can, I try to bring in X and Y, like the X and Y axis. So I'm going to call this my X and I'm going to call this my Y. Okay. So that means that the X is worth 12. Okay. But if the X is worth 12, I should be able to find Y using the Pythagorean theorem, right? So I know that, you know, if this is worth 12, then I know that 13 squared minus 12 squared is equal to Y squared. So this would be what, 169 minus 144 equals Y squared. So then 25 equals Y squared. So then 5 equals Y. Okay, so now we come over here and we put a 5 here. So this is my when information, right? Now let's write down our rates of change. Then what did I use last time? Okay, so we know at 5 feet per second. So we know the base is moving at 5 feet per second away from the wall. So I'm going to call that dx dt, and that's 5, right? 5 feet per second. Okay, so we know that because the ladder is kind of sliding this way, right? The ladder is going this way, so it's sliding down, but then that means that this is going downward. All right, and what are we looking for? We're trying to find dy dt. We want to know how fast the top of the ladder is sliding down the wall. Okay, so now that we're set up, we're all kind of on the same page. Why don't you guys pause the video again and give it a shot, and let me see how you do. Okay, all right. So hopefully you guys have unpaused the video. Let me see here. Where were we? Oh, okay, so we need a formula that relates. We need an equation that relates everything together. Well, we have side lengths of a right triangle. So I know that the Pythagorean theorem would work. So I'm going to say x squared plus y squared equals 13 squared. Now, in the previous problem, I didn't plug any numbers in right away, but in this problem I am, because the length of the ladder is constant. It's not going to change throughout the entire problem. So this will stay 13 no matter how fast the ladder's sliding or whatever. It's 13. I think it's feet per second, or I'm sorry, it's 13 feet long. So this is 13 feet and it's not going to change. So I'm allowed to plug that information in before I take the derivative. That is not when info. Maybe I should put that over here. Constant is c equals 13. Okay, or the length of the ladder is 13. Okay, so now we're going to take the derivative of both sides with respect to t. Oops. Okay, so hopefully you guys got 2x dx dt plus 2y dy dt equals 0. Okay, now we notice that we have a dx dt, but we actually know how much dx dt is, and we know x as well. I'm going to plug in my x. My x is 12. I'm going to plug in my dx dt. It's 5. And then I'm going to say 2y, but we know y is 5. And then we know dx, dy, dt is what we're looking for. So I'm going to subtract this over. So this will become 10 dy dt is equal to, what is that, 120 negative? Divide both sides. And we end up with dy dt is equal to negative 12. Sound good? So that means that the top of the ladder right here is sliding down at negative 12 feet per second at the moment in time when the base of the ladder is 12 feet from the bottom of the house. So that's almost when it's about to hit the ground. So it's going pretty fast at this point, probably the fastest it is because it's been accelerating or it's been increasing its velocity. So that's probably the fastest moment in time. I mean, obviously there's ones right when you hit the ground, but remember, since the base is, or since the hypotenuse is 13, it can only fall, a maximum of 5, and it's basically reaching the peak of its speed right there, or getting close to it. So we end up with negative 12, and you could even put feet per second. Okay, so that's how fast it's falling. And the reason we get a negative, once again, is because it's going downward. All right. Okay, you guys, let me see. Do I want to do another one? No, I think that might be good for now. Yeah, that'll do it for now. I'll make another video with some of the harder ones. These are the nicer ones. There's going to be some harder ones in the next video. Thanks for watching, you guys.